Greetings peeps! This is a look at elastic collisions. And elastic collisions adhere to two things, two principles. First of all, there's the conservation of linear momentum. And in that, the total linear momentum is conserved. That's exactly what we would expect for any two objects that don't have any external forces acting on them, only the internal forces of their interactions. What we have for an elastic collision is that total kinetic energy is conserved. It is also conserved. Its counterpart, the inelastic collision, does not have kinetic energy conserved, but it is here for the elastic collision. Okay, so let's take a look at what that means. We'll check it out from the perspective first of conservation of linear momentum. So we've got P naught equals P final. Momentum original equals momentum final. So here's the momentum original on this side. M1 V1 naught plus M2 V2 naught equals, on the other side, M1 V1 final plus M2 V2 final. This is purely a restatement of the conservation of linear momentum that we've seen before. Now for kinetic energy. Kinetic energy naught equals kinetic energy final. Okay, original equal final. And the variables, the relationship between kinetic energy and the variables of mass and velocity, as we remember, is 1/2 mv squared. So we've got 1/2 m1 v1 naught squared, quite a lot to say, plus 1/2 m2 v2 naught squared, plus 1/2 m1 v1 final squared, plus 1/2 m2 v2 final squared. Okay, well, there's a whole system of notice-bien that goes through the combination, the crazy algebra. There's quite a bit, it's quite extensive, but it's for you to follow. It's actually a couple pages worth of algebra. Peruse it, check it out. You know, it's good to see where this came from. If you can track it, that's wonderful. We're going to just use the final results, and I'll show you what they are. But before we do that, I want to discuss the action. What happens? Okay, the action here is that objects either bounce perfectly and away. Let me get on the other side so you can see that again. Again, that's objects either bounce perfectly away from each other if objects have the same mass and one is stationary. Okay, so this situation here is we're looking at an action if one of them is stationary. That's what we're going to model. That one of the objects is stationary and the other one is moving, and they're purely elastic in terms of their collision. So what happens in that case? Later, we'll be able to extrapolate that using relative velocity. We'll be able to handle problems where both objects are moving at each other with some velocity. We'll be able to model what happens with elastic collisions also. All right, so now what happens here is that in some cases, momentum and kinetic energy is fully transferred by the moving object. Okay, so they either bounce perfectly away or there's a full transfer of momentum and energy into the other object. And we'll look at those conditions to see what happens there. So we can think of like some of these in terms of billiard balls. Billiard balls are a pretty good approximation of elastic collisions. And so that's what we use to model what we see. All right, so coming up next are the equations that define the elastic collision in terms of original velocities. Woo! Alright, and so here we have our case study of elastic collisions. Our case study involves a situation where ball 1 with linear momentum smacks into a stationary ball 2 in a 1D elastic collision. So here's the picture of that. We've got ball 1 headed towards ball 2 being stationary. Ball 1 has velocity v1 naught, okay, and they both have some certain mass. We'll look at what happens when the masses change and what are known as boundary conditions. We'll set extreme values to understand the totality of the system. All right, so what are the velocities of ball 1 and ball 2 after the collision? Well, again, the notice-bien has the derivation of these formulas, and it is some pretty intense algebra for this situation. And what we have is the end result. So in terms of v1 naught, m1, and m2, v1 final is v1 naught times the product of the parentheses here, which is m1 minus m2 over m1 plus m2. Almost looks like the Awad's machine, kind of a coincidence there. has nothing to do with it, but it just turned out that the format is pretty similar. V2 final is V1 naught times 2m1 over the sum of the masses m1 plus m2. Okay? So next we'll look at the boundary conditions and see how they behave when we change the values of the masses to the extremes. Okay, hang with me. Alright peeps, let's continue our case study by looking at some boundary conditions. Boundary conditions are situations where we look at the extreme values and a nominal value in the middle and we kind of see what's going on. Alright, the first condition is that m1 is way, way bigger than m2. m2 is tiny, tiny, tiny compared to m1. m1 equals m2. Alright, that's the nominal condition in the middle. And so we have also m1 is really, really small compared to m2. So we're going to look at these extremes to kind of understand the behavior of the system overall and what it means. Alright, in the first case, we've got V1 final equals V1 naught. And the first equation for this situation where again the M1 is moving and M2 is stationary, we've got M1 minus M2 in the numerator and M1 plus M2 in the denominator. So if you look at your notes from the previous slide, you can follow along with this equation, okay? And so what happens is that M1 is so much greater than M2, we can ignore the M2. We can pretend it's not there, and so we get M1 over M1 in that particular ratio. Okay, so M1 over M1 is 1, and so we have V1 final equals V1 naught. So in effect, when M1 plows into M2, its velocity is unchanged. It just keeps going at the same velocity. Well, what happens to M2? Well, if we look at the next equation, we see that there's a 2m1 in the numerator, okay, so we get 2m1, and the denominator is m1 plus m2. We can ignore the m2 because it's so tiny, so we have 2m1 over m1. m1's cancel, and what we have here is v2 final equals 2 v1 naught. So this is not quite as intuitive. We might expect that because m2 is so much smaller than m1 that it is going to be kicked and it's going to move faster, but how much faster? It's actually twice the velocity of m1. So as an analogy, imagine you have like a little pebble, and that pebble is let's imagine it's stationary and a bus is coming and its windshield is elastic, let's say, and it smacks into the pebble. Well, the bus will be unaffected by that pebble. It won't slow down as a result. It won't feel any change in its velocity, but the pebble will shoot forwards at double the velocity of the bus, which is a weird thing. That's not so intuitive that it's going to go at twice the velocity, considering that this is a purely, perfectly elastic collision. Alright, next situation, m1 equals m2. Alright, so we have m1 minus m2 in the numerator here, and if two values are equal and you subtract them, you get 0. So it's 0 over 2. So V1 final is 0 meters per second. So what happens in this case is M1 is going to be stopped when it collides with M2. Well, what about M2? What is it going to do? What's its velocity going to be? Okay. Well, we've got 2m1 over m1 plus m2. Okay. So 2m1 is 2, and m1 plus m2 is also 2, so 2 over 2. So it's 1 over here times V1 naught. So V2 final is equal to V1 naught. Okay, so what happens is that V2 final assumes the velocity that V1 naught had. Okay, so essentially what happens here is that M1 plows into M2, M1 stops, and M2 assumes the velocity that M1 had. So it has the same momentum and kinetic energy. There's a full transfer from M1 to M2. You've actually seen this before if you've ever played a game of billiards, pool, all right? It's a simple shot where you take the pool cue and you fire the cue ball straight on into another ball. I mean, one-dimensionally straight on the table. No angles, no English, nothing like that. Just straight, and what happens is that when the cue ball strikes a ball directly in front of it, the cue ball stops and the other ball moves forward at the velocity that the cue ball had. So you've seen this many times. Boonk, clock, ink. That's basically it. Okay, so cue ball and ball, other billiard ball, is that situation here as described mathematically. So that's intuitive and the math does support that. Billiard balls are fairly elastic, so that's why. Last case, M1 is way less than M2, M2 way bigger than M1. So in the numerator, we have M1 minus M2. This time, we can ignore the M1s. So it just becomes negative M2 over M2. And so what this says is that when M1 plows into M2, it's so much smaller, it's just going to ricochet right off. It's going to go at the same velocity in the opposite direction. It's like that pebble hitting a wall. All right, the pebble's in motion and the wall is stationary, and it's a fully elastic collision, and the pebble just ricochets off the wall. Kind of, that's somewhat intuitive in that it's just going to bounce backwards. What about V2? What about the massive M2 that is staying still? Well, it kind of becomes the immovable object because M1 is so small, it's in the numerator, and 2M1 is almost nothing. So we're going to just basically approximate that as 0. Anything that's M1 is 0, and in comparison to M2, so we have here at the extreme that V2 final equals, well, 0 meters per second. It's the immovable object. It's not going to move at all. Here's why. The inertia of M2 is so great that that tiny little bombardment by the pebble did not budge it at all. You need more M1, a bigger force in that collision, essentially, for M2 to begin moving. So M2's inertia is so great. That's what it is. All right, those are the cases, and that is the elastic collision for the situation where we have one of the objects stationary. In another video, there will be the case where we have two objects in motion, and we'll be able to handle that actually with the same equations, but using principles of relative velocity. Rather than derive whole new sets of equations that become even more complex, we can use a little trick with relative velocity. So that's what it is. Elastic collisions. Morad, out.